Welcome to Calculus. I'm Yui Pragma. In this lesson, we'll be talking about what calculus is about. There are two different problems that motivate calculus. The first of these is the tangent line problem. This is straightforward to explain. Let's suppose we're looking in the XY plane. It doesn't really matter whether we're looking in the first quadrant or any other quadrant. Let's suppose we've got a function f whose graph is a curve. Let's pick a point on the graph of f. And now let's draw a straight line that touches the graph at exactly that spot. It might look like the white line is touching the black curve at more than one spot, but we're imagining the white line touches the curve at only the one white spot. Such a line is called a tangent line. So here's the tangent line problem. What's the slope of the tangent line? In other words, the line can be written as y equals mx plus b. The number m, that's supposed to be rise over run. What is m equal to? That's the tangent line problem. Why are we interested in the tangent line problem? If we have a straight line, then that line has a slope, meaning rise over run. The slope of a line is its rate of change. If the slope were 2/3, then the rise would be 2 and the run would be 3. If we were walking up the line from left to right, then for each 3 units we move to the right, we'll move 2 units up. That's what rise over run means. If we have a smooth curve, and then pick a point on that curve, and then find the slope of the tangent line, then we can say that the rate of change of the curve equals the slope of the tangent line. Notice that we're talking about the rate of change of the curve at the one point. If we choose a different point, then we'll have a different tangent line, so the rate of change of the curve will be different from point to point, but this isn't as big a deal to handle as you might think. So anyway, we've got the xy plane, the graph of our function f, some point on that graph, and the line tangent at that point. What we can do is take f, run it through a process called differentiation, and then get a new function called f prime. This new function is called the derivative of f. The point we chose has an x-coordinate, let's call it a. If we take a and plug it into f prime, then we get out the slope of the tangent line. And we can use this same function f prime no matter which point on the curve we choose. So that's an explanation of one of the two problems which motivate calculus. What about the other one? That's called the problem of the area under the curve. Let's take a look at the xy plane again. And let's suppose we have the graph of a function f. In this case, it is important that we're looking in the first quadrant, but that's not a detail we need to worry about right now. Let's pick 2 points on the graph of f. Those points have x-coordinates, let's say a and b. So here comes the area under the curve problem. What's this area under the curve? Can we figure it out? Note that the left side, the right side, and the bottom of the figure are all straight edges. The issue is the top edge. The function f can be just about anything. In many cases, not all cases, but many, we can take the formula for our function f, run it through an operation called integration. This long stretched out s right here, this is called the integral sign. Anyway, the result of integration will be the area under the curve. Note how a, b, and f all show up in this doodad. So those are the two problems which motivate calculus, and believe it or not, they're connected to one another. Here's a quick explanation of how. Back in the tangent line problem, we had our function f and the line tangent at the one point. We took f, ran it through the differentiation process, and got f prime. F prime is what can tell us the slope of the tangent line. Now let's change problems. Let's suppose we've got this curve. We want to know this area, and the curve is the graph of f prime. Not f, f prime. If that's the case, then this gobbledygook, which is supposed to tell us the area under the curve, is equal to fb minus fa. This f. In order to figure out all this, we need to start with f prime, run it through a process called anti-differentiation, and that'll get us f, which we can then use down here. This equation right here, this is the fundamental theorem of calculus. So those are the two problems which motivate calculus and a quick explanation of how they're connected. There are some key words that I'd like to point out. When we talked about the tangent line problem, we talked about the operation of differentiation, and the result we got from that was the derivative. Roughly speaking, anything to do with differentiation is called differential calculus. When we talked about the area under the curve, we talked about the integral sign, which was that stretched out s. The integral sign usually indicates the operation of integration, but it might indicate a different operation, which is anti-differentiation. And the result we got from that was the antiderivative. Roughly speaking, anything to do with integrals and anti-differentiation is called integral calculus. Differential and integral calculus are linked by the fundamental theorem, which I mentioned a minute ago. I have the feeling your head might be swimming, so I'll talk about how calculus is applied in later lessons. Right now, I want to give you an important warning about your first calculus course. Most math courses have a difficulty curve which looks like this. Week by week, the course gets harder. This is also true of Calculus 1, except at the very beginning. This little spike right here in difficulty is due to the definition of limits. Limits will be used to define differentiation and integration and so on. The mere concept of limits is no big deal. The challenge level of the concept itself is back down here. The trouble is with the strict mathematical definition of limit. That's usually a mind blower for students who haven't seen it before, and if you feel overwhelmed by it, that's totally normal. You'll get through it in a week or two, and things will go back to normal. No problem. Okay, so you've made it to the end of this introduction to calculus. There aren't any homework problems for this video, but I've got a reward for you, which is the most important result calculus has ever provided to the world in history, which is the following mathematically optimized and empirically validated pickup line. Hey baby, I'd like to be the area under your curves. Okay, thanks for watching. Like, comment, subscribe. See you in the next video.